Before we look at the main content of this video, let's review the fundamental result that we'll be using throughout this video. It is the Basic Proportionality Theorem. To illustrate this result, we're going to make use of this figure down there. And suppose we're looking at the triangle ABC, and DE is a line parallel to the third side, AC. And it intersects at AB and CB at the points D and E. Then we can conclude that BD over DA is equal to BE over EC. Okay, let's move on to the first result. This is a corollary of the Basic Proportionality Theorem. It says that if a line parallel to one side of a triangle intersects the other two sides in different points, then it cuts off segments that are proportional to the sides of the triangle. To illustrate this theorem, we use the figure down there. In this figure, the line DE is parallel to AC, just as in the Basic Proportionality Theorem. Then we would like to show that the length of BD over the length of BA is equals to the length of BE over the length of BC. Let's take a look at the proof. We will combine the Basic Proportionality Theorem with a little bit algebraic manipulation. The first observation is, by the Basic Proportionality Theorem, BD over DA is equal to some scalar k, which is the same as BE over EC. As a consequence, we must have DA equal to BD divided by the scalar k, and EC equal to BE divided by the same number k. Now let's try to compute the ratio BD over BA. However, we observe that the side BA is in fact the union of BD and DA. So we could simply write up the length of the sides BA as the length of BD plus the length of DA. However, with our last observation, DA is equal to BD over K. Hence, we could substitute the expression in terms of BD into the place of DA. And some algebraic manipulation leads to the fact that the outcome is equal to 1 over 1 plus 1 over K times BD for both the numerator and the denominator. And surely these two BD would cancel each other. Hence, we conclude the ratio between BD and BA is precisely 1 over 1 plus 1 over K. Let's do the same thing for the ratio between BE and BC. We also observe that the sides BC is the union of BE with EC. Hence, we could replace the length of BC by BE plus EC. Then we go through the similar argument that EC is equal to BE over K. Hence, the denominator could be replaced by 1 plus 1 over K times BE. And the numerator is still just B. And you could put a 1 over there to emphasize. The numerator is equals to 1 times B. Now, by canceling those two B, what we end up with is the same ratio, 1 over the sum of 1 and 1 over K, which is precisely the ratio between BD and BA. And this is what we like to prove in this part. The second result is indeed the converse of the last theorem. It says that if a line intersects two sides of a triangle in different points so that it cuts off segments that are proportional to the sides, then the line is parallel to the third side. Just as in the figure down there, if we know that the ratio between BD and BA is equal to the ratio between BE and BC, then the line DE, which is this line cutting the triangle at two sides, would have to be parallel to the third side, which is AC. The proof of this theorem is a practice of proving by contradiction. Hence, we will begin the proof with negating the result. Namely, we will suppose the line DE is not parallel to the third side, AC. On the other hand, by the Euclidean parallel postulate, there is a line through the points D, which is the point up here, and we're going to denote this line as DF, for instance. And the characterization of this line is that it is supposed to be parallel to the third side, AC. To elucidate it, we can draw a line on the figure up here. And by the task axiom, the line DF, which intersects the triangle at a point between A and B, would have to be intersecting a point on either BC or AC. But by assumption, DF is parallel to AC, so it would not be intersecting AC at all. Therefore, it must be intersecting some points in between B and C. And for the sake of convenience, we will simply denote the intersection as the point F. In other words, by the Pascal's axiom, DF intersect BC at, say, F. Consequently, according to the last theorem, we must have the following result, which is BD over BA. It's equal to BF over BC. But recall that BE over BC is also equal to BD over BA. That is, we conclude that BE over BC is the same as BF over BC, since both of them are equal to BD over BA. Now, what we have on the left-hand side is a quotient with BC as a denominator, while the quotient on the right-hand side also has BC as a denominator. Therefore, we must have the numerator being the same. However, this is a contradiction. Why? Well, because both F and E are on the ray BC. According to the ruler postulate, we only have one point on the ray BC such that the distance between B and the given point is of the given distance. And in other words, we should not have two distinct points that is of the same distance from B on the ray BC. So that turns out to be a contradiction. To the ruler postulate. And if there is a contradiction, the negation of the result must be false. Hence, we conclude that DE must be parallel to AC. And that's our proof here. Thank you for watching. See you next time.